In the last session, we talked about different ways of sending money. We said that we can use transfer or send or call. And we also mentioned that using call is preferable in general. And I told you to look at Solidity by example. So here you can see the different ways of sending Ether, and again, all of the things that we covered in the previous session. And it also tells you what happens with the receive and fallback functions. I have covered this as well. Now, one point that I want to mention today is this idea of pull over push. So the idea is that whenever you want to pay someone, instead of having a function in your contract that just pays them, it's better if you have a function that the payee can call to basically pull their money out instead of pushing the money to them. What do I mean by this? Well, remember this contract that we had, which was basically a joint account, and it had a deposit function, so anyone could deposit. We now know that instead of the deposit function, we can just have a receive function. Or if we don't want to even have a receive function, we can just have a fallback function, which is external and payable, right? But then we had this withdraw function here. And as you see, it was transferring money to both Alice and Bob. So the idea here was that this is a joint account. So whatever the balance of the current account is, half of it should go to Alice and the other half should go to Bob. Now, we've seen that transfer is not a great way of doing this. So instead, we want to send using call. So let me just copy this. And instead of saying, I want to transfer the balance of this contract to Alice, I can just do something like this. I can say, I want to send to Alice a value which is basically the balance of this contract divided by 2. So address this dot balance over 2. And I'm calling the empty function, which basically calls the fallback function of Alice if Alice is a smart contract. And if Alice is an externally owned account, I'm just paying her this much, right? And we talked about this before. We receive a Boolean, and then we can figure out what to do with that Boolean value. Now, I'm not going to have this requirement here, because if I have this, then it will just revert the entire transaction whenever sending money fails. Instead, I just say it's Alice's responsibility to make sure she can receive the money. Okay? And then I go and transfer the rest of the money to Bob. So I'm going to just copy the exact same thing, except that here I say I'm calling Bob, and of course I'm giving Bob the entire remaining balance. Okay, I have to give this some other names of send to data to. Okay, so this is now my withdrawal function. But again, as you can imagine, there are many different ways to attack this. So for example, this function can be called by either Alice or Bob. Okay. Now, suppose that Bob is not ready to receive the money for some reason. For example, Bob is a smart contract. There is a bug, let's say, in the smart contract, or he doesn't expect to receive the money, so the receive function is not ready. All sorts of things can happen. But then Alice can call this withdraw function, and she can basically force the payment to Bob, right? And again, maybe Bob is not ready for it. It can create all sorts of bugs. So here's what Alice can do. Suppose that Bob wants to withdraw the funds. So Bob wants to take out his money. So he tries to call the function withdraw. But let's say that Alice is a smart contract. And then let's say that she has a fallback function or a receive function, which basically wastes all the possible gas. So this is the contract that Alice has used. So I'm calling this one Alice attack. And let's say that Alice has used this attack contract to sign up in this joint account. So in the joint account, whenever I'm talking of Alice, I'm actually talking of an instance of this attack contract. And let's say that it has a fallback function. And let's say this fallback function just wastes a lot of gas. So the only thing it does is running an infinite loop. So I don't know, while 1 is greater than or equal to 0, do something here. So just keep doing something stupid just to waste all the gas. Okay. Now, what happens if Bob calls the withdraw function here? Basically, it checks that the message sender is either Alice or Bob. The check passes, and then it tries to send half of the balance to Alice. But this half is sent to Alice by a call, and it's a call to the empty function. So there is no such function. The fallback function of Alice will be called. And then the fallback function of Alice runs out of gas, right? Because, I mean, this is a function that just has an infinite loop. There is no way it doesn't run out of gas. It doesn't matter how much gas we have allocated, it is going to run out of gas. Okay. Now, what happens when this fallback function runs out of gas? Well, it's going to throw an exception, but we said that the exceptions will not be propagated when we're using call, right? So in this case, the execution of withdraw can continue, but this sent value just becomes false. But the more important problem here is that there is no gas to continue this execution, right? Because this call to Alice shared all the gas with Alice's fallback function, and Alice's fallback function has already used all the available gas. So now there is no gas to use for the next call to pay Bob. So the withdraw function also runs out of gas, and running out of gas is an exception. So the withdraw function is also reverted. So you see, even though we said that we use call to make sure that this reverting of functions or throwing of exceptions are not propagated, in the case of gas usage, we can still have these kinds of attacks. Because basically gas is a resource and Alice can spend all of that resource and then Bob cannot have any access to it. Now, again, as usual, the way this would work is that Alice can enable or disable her attack. So usually there would be a Boolean here called attack, which is, let's say, true. And then the fallback function says, if we are currently doing an attack to this file, right? And then there would be another function that can only be called by Alice, and it can disable the attack. So let's say function, I'm going to call it toggle attack. This is public. And I'm going to say only Alice can call it. So I'm going to require that msg.sender is Alice's address, whatever her address is. This is Alice. So I only allow Alice to call toggle attack. And all it does is that it changes the value of attack. So if attack is true, it becomes false. Otherwise, it becomes true. So now if I have this kind of contract as Alice, I can control whether my fallback performs an attack or not. And as long as I say that my fallback performs an attack, Bob cannot withdraw his funds from this joint account, because whenever Bob calls this function withdraw, all of the gas will be used by the call to my fallback function, and then there is nothing remaining to send the money to Bob. Okay, so because of this, it's really important that you never pay someone in a function that is called by someone else. So the idea is that if you want to pay Alice, make sure that Alice is the one calling that function. If you want to pay Bob, make sure that Bob is the one calling that function. Okay. Now, how can I do this? Well, basically, I can keep track of how much money I owe to each one of them. And I mean, in general, if you have more than 2 people, then you can have an array or you can have a mapping. But in this case, I have just 2 people, Alice and Bob. So I can just keep track of how much of the money belongs to Alice and how much of the money belongs to Bob. So let's call this Alice's money and Bob's money. Okay. Now, whenever someone pays us, so in this fallback function, when we are paid, we just say that half of the money goes to Alice and half of the money goes to Bob. So how do I do this? Well, I would just say Alice's money increases by whatever value we got, value over 2. And also Bob's money increases by the same amount. Now, I'm assuming that the value is even. Of course, you can figure out what to do if it's odd, but it doesn't really matter. Okay, now, when someone calls the withdraw function, instead of paying both people, we're only going to pay the person who called the withdraw function. Okay? So I say, first require that only Alice or Bob can call this. And then I'm going to say, if it was Alice who called it, then pay Alice. Okay? But how much should I pay to Alice? I should just pay Alice's money. And similarly, if it was Bob who called it, then just pay Bob. And again, here, I'm not going to pay the entire balance of this contract. I'm just going to pay Bob's money. Now, why is this a better solution? Because whenever someone is calling withdraw, they're the only one who's paid. So they cannot do any kind of attack now. If Alice calls withdraw, I'm only going to call the fallback function of Alice. So if she does any kind of attack, it's only going to affect herself. Similarly, if Bob is calling withdraw, I'm only calling the fallback function of Bob. So just make sure that this is always the case in all of your contracts. Make sure that instead of having person A calling some function and then person B getting paid, you always just store the amount of money that you have to pay to each person, and then you ask them to call the withdraw function themselves. And then the person who's calling the function is the same as the person who's getting the money. And of course, we transfer money using call. We don't use transfer percent. Okay. So now I want to talk about a different use case. And I want you to consider this idea. Suppose that I want to create a lottery. So I want to create a contract in which anyone can sign up and basically buy a lottery ticket. And then I want to randomly choose one of the tickets uniformly at random. And then I want to give all the money to the person who purchased that ticket. Okay. So let's try to write something like this. Okay, I'm going to call this one lottery.sol. And again, just as before, remember that you should always start by saying what is the version of the compiler that you're using. And then let's write a contract. Let's call it lottery. Now, what do I want? I want anyone to be able to register. So let's say I have a function called register, and this is public and payable. And let's say that you have to pay a particular amount to register and buy a ticket. Or actually, I can also call it buy tickets, right? So let's call this one buy tickets. And I just say require that the amount that is paid, msg.value, is some amount, whatever the price of the ticket is. So 1, 2, 3, 4, let's say. Okay, so this is the amount. And then, of course, I want to keep track of who owns every ticket. So let's say I have a mapping. You can also have an array, but I just say I have a mapping from uint to address that basically tells me who the owner of every ticket is. And let's say I also have a uint n, which is the number of tickets. Okay. So when someone wants to buy a ticket, I first increase n. And then I also say that the owner, actually, before increasing n, I say that the owner of n is whoever sent this message. So msg.sender. Okay. So this is very simple. You just buy a ticket, and whenever you buy a ticket, you're increasing n, and your name is also getting added to this owner map. Well, not your name, but your public key, your address. Okay. And this can be used by either externally owned accounts or by smart contracts, that's completely fine. And the tickets are numbered from 0 to n-1. So now I want to just pick a number from 0 to n-1 uniformly at random. So let's say I have another function. Let's call this pick winner. And this is also public. Now, how do I actually generate a random number? Now, this is a big problem because if you think about it, everything on the blockchain has to be deterministic. We talked about consensus, right? So we said that whenever there are function calls and so on, everyone on the network is going to run them. And everyone on the network has to reach the same result. Everyone has to have the exact same run of the contract, and they should basically reach consensus about the state of all the variables, right? So I cannot have a random number generator here, because if it's really random, then, or even if it's pseudo-random, different people on the network would generate different random functions and then different random values, and then they would not reach a consensus. So I have to somehow pick a random number, but I have to also ensure that this random number is subject to consensus. I have to make sure that everyone on the network is picking the same random number, because everyone on the network has to agree who the winner of this lottery was so that the winner can be picked. Okay, well, how can I generate such random numbers? Well, one of the basic things that we can do is to use the hash of the current block, right? So I can do something like this. I can say, let's take some number h, which is just the hash of the current block. Now, how do I get the hash of a block? I can just use block hash, but then I have to give it the block number, okay? So, and how do I get the block number? Well, it's just block.number. So if I want the hash of the current block, I can just say block hash block.number. Okay. Now we have a typecasting error here because it says that this one is not a uint, but h is a uint. So I have to explicitly convert the type. Okay. So now I have this number h, which is basically the hash of my current block. And then I just say the winner is the person who had the ticket number h. But of course, I cannot take h itself. I have to take h modulo n. Okay, so I just say address payable winner is payable owner of h modulo n. Okay, and then I just pay them. So winner.transfer address this balance. Okay. Now we have tons of problems here. The first problem is that I'm transferring this money to the winner, and I'm not checking that the winner is the person who called this function, right? Because of course this function is the one who's even finding the winner, so it's actually very unlikely that it was called by the winner himself. So I have to make sure that this doesn't happen. And of course, I'm also using transfer, which is bad. I have to use call. Now, let's fix those things. So how do I fix it? Well, I'm just going to have an address payable called winner here. And then I just do this. I say that the winner becomes the person who owns that randomly chosen ticket. And then I can have another function called withdraw, which is also public. But I say that this function can only be called by the winner. So I say require msg.sender is whoever won here. And then I'm just going to pay them. So I'm going to say winner.call, and the value is going to be the entire balance of the current contract. So address this balance, and the function I'm calling is just the empty function. Now, in this case, I can also check if sending money to the winner was successful. So I just say bool send, and then I have some data. I don't care about that. What's wrong here? Okay, I cannot call it underline. Okay, so I just say require that the send was successful, and if it was not successful, just say, I don't know, sending ether through an exception. Okay. Now, we still have a lot of problems. One problem here is that people can call these functions as many times as they like and at any time, right? So, for example, suppose that someone calls pick winner and they're not chosen as the winner. They can just call pick winner again. Okay, so let me actually write an attack like this. So let's actually say that winner is public. So I can have an attacking contract. And let's say that my attacking contract first buys a lot of tickets. So it buys, let's say, half of the tickets. Okay. And afterwards, it just keeps calling pick winner until it wins. Okay. So I'm just going to have a function called attack here, public, and, or, okay, let's call this f. It's a function f that is public, and I'm just going to take this lottery. Let's say I have already bought a bunch of tickets in it. So I'm just going to call the function pick winner over and over again until I'm the winner. Okay. So let's say I have the address of the lottery contract as well. And here I say lottery, I don't know, let's call it my lottery is the lottery at this address. And then I just say, as long as I am not the winner, is not the current contract, just keep calling pick winner. And then, of course, at the end of this while, I would become the winner. And when I am the winner, I would finally say that just call withdraw. Okay. We have a bunch of small errors here. We can fix that. So I think this is like, yeah, okay. So I'm basically just checking over and over again, am I the winner right now? And if I'm not the winner, I'm just calling pick winner again. And imagine that if I have half of all the tickets, then on average, I would have to call pick winner twice before I become the winner, and then I'll win. But actually, this attack doesn't work. Why doesn't this attack work? This attack doesn't work because when I'm doing the pick winner, this number h is just the hash of the current block, right? And because it's just the hash of the current block, and because this entire attack is run in the same block, it's in the same transaction, it's going to just pick the same winner every time. So this is not really going to work. What's going to work is if you call pick winner in different blocks over and over again. But imagine if I had something else here. So imagine if I had some x here, and I would just say that I add this x. Now, here I could do something similar. I could just give the x over and over again, and I could just try different values of x, okay? So I can just say do this, and my I is initially 0, and every time I increase I, okay? So basically my point is that if someone can generate random numbers over and over again, they can do it until they win. Now, you might be able to do this in just one block with one transaction and one external attack contract, or you might need to do it in many different transactions. So that's the first problem. The second problem is that we don't really have any time controls here, right? So it's possible that someone calls withdraw before even pick winner is called, right? It's possible that someone calls buy ticket after pick winner is already called. So if pick winner is already called and we already know who the winner is, no one should be able to keep buying tickets, because that's definitely some sort of a mistake. They shouldn't be able to buy tickets when someone else has already won, right? So we want to do some time controls. And the way we do time controls is by checking the block number. So for example, I can say here that the block.number should be bigger than some number, let's say 1000, and it should also be smaller than some other number, let's say 2000. So this would say that the buy ticket function can only be called in the blocks from 1000 to 2000. And because we know that we will have a block, well, in Ethereum, it's every 13 seconds or so, I can actually use the block number to control for time. Now, these block numbers are too small. If you want to see actual Ethereum block numbers, you can go on Etherscan. And you can see that these are the latest blocks. So this is a block that was mined 8 seconds ago. This was a block that was mined 20 seconds ago, and so on. So this is like the current block number. I can just put the block number here and let's say plus 1000. Or another thing I can do is to just use my constructor function to keep track of the time when the lottery was deployed, okay? So I'm going to have something called deployed block number, which is basically just going to save the block number in which my lottery was deployed on the blockchain. So I have my constructor here, and I just say that the deployed block number becomes block.number. Okay, so whenever the lottery contract is put on the blockchain, at the same time as deployment, the constructor is executed, and then I know the deployed block number. And then here I can say that buy ticket can be done from, let's say, when the contract is deployed to, let's say, 100 blocks after that. So deployed block number plus 100. Okay, so this is how I can do time control. And then I would put similar things for pick winner. For example, here I say that you can call this only after that first period is over. So only after block number is more than deployed block number plus 100. And also for withdraw, I can say that you can call it only if pick winner has already been called. So maybe I can also have a Boolean. Again, I could also just have block numbers in withdraw. I just want to show you different ways of enforcing times. So I can have a Boolean that tells me whether a winner was picked. And when I pick a winner, I set this to true. And then in withdraw, I require that the winner is already picked. Okay. Great. So this solves our timing problem, but we're still a far way from having a good random number generation here. Now, what is the problem? Who can do an attack? So let's say that you have deployed this lottery, and let's say that it's a very famous lottery contract. Let's say millions of people have taken part in your lottery. Who can do an attack here? Any ideas? So the problem is here. We are basically using the block hash as a random number, but the block hash is under the control of the miner, right? So if I'm the miner of the current block, I can easily include or exclude some transactions, and that would change the block hash. So if I'm a miner and I'm also taking part in this lottery, let's say I'm a miner and I also own half of the tickets in this lottery. I create my block, I check whether I'm winning the lottery. And if I see that I'm not winning the lottery, I would just ignore the block and create another block. Okay, so the miners can actually control this. Or at the very least, if I'm not winning it, I would just not include the transaction that has pick winner into my block. And that would give me more chance. Maybe in the next block, I would win. Okay. So even being able to tamper with your probability of winning it, the lottery is, of course, considered cheating. And in this case, all the miners, well, at least the miners of the blocks in which pick winner can be called, can actually cheat. So you have to be very careful that whatever contract you write is not at the mercy of the miners. You should never give miners any kind of control over what happens in your contract, which also includes using the block hash or any other property of the block as a source for random number generation. These are not random because they're under the control of the miners. Now, if you look at the global variables, there are many other things that you can use as well, but like, I don't know, you can use the transaction gas price, you can use a lot of other things, but all of these are controlled either by the miner or by the person who's creating that transaction. And the only difference is this one. We will talk about this in a later session. This is actually one way of generating random numbers. But for now, we want to continue and see how we can generate random numbers. So this idea didn't work. We cannot just use the miners to give us random numbers. What else can I do? Well, there are some oracles that give you random numbers. For example, there is this website, I think random.org, and there is an oracle that takes random numbers from this website and puts them on the blockchain, and then you can use that. But of course, the problem with using an oracle is that an oracle is basically someone who's taking some data from outside of the blockchain and writing it on the blockchain, let's say in a smart contract, and letting other people access it. Do you really trust that person? We don't want to trust anyone. Again, in this course, our main objective is to create trustless protocols. So we don't trust the oracle, we don't trust the creator of the oracle, we don't want to use these kinds of services. We want to basically generate our random number on the blockchain itself. Okay, so how can I generate a random number? Well, one really nice idea is that I can say whenever you buy a ticket, you have to also contribute to the generation of the random number. Okay. Now, what does that mean? Well, it means that whenever I buy a ticket, let's say that I also give some number x. And then all of these x values are going to be summed up together, and we're going to use the sum of these x values as our random number. Okay. So let's try doing this. I have this x value here. And let's say I also have a mapping, which basically maps every ticket number to its x value. I call this one big X. And when I say that the owner of the nth ticket is msg.sender, I say that the x value is also small x. Okay. So I just save this. What's wrong here? Oh, sorry, this was unsigned int, that was int. So Solidity is very picky about types. It doesn't really convert things. Okay, so now I do this, and when it comes time to pick the winner, instead of saying that H is the hash of the current block, I just say that H is the sum of all these X values. So I just have a for, and I say for every I from 0 to n, increase H by xi. Okay. And again, as usual, what's happening here? Okay, it's again the problem with int and uint. So I just sum up all of these numbers. I sum up all the numbers that were given to me by the participants. And then I take the result modulo n. And I say that's our winner. Okay. Now, if you think about this, even if I have one participant who was honest and was actually giving me a random number, if I have even one participant who was choosing this value of x uniformly at random, then the result, the sum modulo n, is also going to be a uniform random number, right? So that's great, because that means that no one can really cheat here. But we have bigger problems, right? And our bigger problem is that everything on the blockchain is public. Remember when I was talking about functions that are public, and what I said there was that everyone can see everything. But when I say that a function is public or when a variable is public, that just means that other contracts can call it or can see it, right? So here, everything that I have in my lottery contract is public knowledge, because of course it's subject to consensus. So everyone knows about this mapping owner, everyone knows all the X values. Anyone who has access to the blockchain is seeing all of the transactions and is actually keeping track of all of these values, right? So when you're buying a ticket, you already know all the previous X values. And because you already know all the previous X values, you can choose your X value so that you become the winner later on, right? So if I write a smart contract like this, basically the winner is always the person who buys the last ticket. Because if everyone is rational, if everyone just wants to maximize their own payoff, and if everyone is really smart, they would figure out what value of X they can use here to become the winner. And whoever calls buy ticket last basically wins the whole thing. So it's not really random. It's just a matter of who gets to have the last transaction in the last buy ticket transaction. But again, this is giving power to miners as well. So our problem is not just that it's not random. It's also that, again, miners get to decide who wins here, because miners get to decide which transactions get added to the blockchain. Okay, and especially the miner who's mining this last block, they're the ones who get to decide who calls buy ticket last. Okay, so this is not good. And again, the reason this is not good is because everyone can see everything that you're saving in a smart contract. And now, just one other point here is that this is also the reason why we would never save a private key in a smart contract, because as soon as you save something in a smart contract, it's public knowledge. And a private key has to be private, so you should never save a private key in a smart contract. Okay, let's see, what can I do here? Well, instead of just giving my X value, I can maybe have a commitment scheme. Maybe I can say that I just give the hash of my X value, and then I give the X value later. Okay, so when I'm buying a ticket, I'm just going to give the hash of my X value. So let's do this. Let's say I have another mapping, uint to uint. I'm going to call this C for commitment. And here, what's happening is that instead of giving my X value itself, I'm just giving a C value and doing this. Okay. So again, C is the hash of X. So later on, I want to verify that I gave the correct hash. Basically, I want to show my value of X. I want to reveal, like in a commit reveal scheme. So let's say I have a function called reveal X, or just reveal, and it takes, let's say, a ticket number, and it also takes some value of X. And what this does is that it just checks. It says, let's take the hash of X, and if the hash of X is equal to the C value for this particular ticket number, then say that the X value for this ticket number is X. Otherwise, don't do anything. Now, I have a compiler here because I'm just writing hash. Of course, you can use whatever hash function you want. Okay. And of course, I'm also going to have time checks here. So I'm going to say that you can reveal only after, let's say, 100 blocks and only before 200 blocks. And then later on, when the winner is picked, it has to be after everyone has revealed. Okay. So now this sounds much better, right? So everyone can come in, they can buy a ticket. When you buy a ticket, you're just giving the hash of your X value. You're just committing to some value, but no one else is seeing this value, right? Because only its hash is saved in the smart contract. This is a hash, right? And then later on, like between blocks 100 and 200, you get to reveal your hash. You get to basically give the X value that had that hash, and then that X value is saved. And finally, when we do pick winner, we're just going to sum up all of the X values and take that measurement. So this avoids the problem that we had before, because when you're buying a ticket, you don't know what the X values chosen by the other people were. You just know the hashes of the X values, and that doesn't give you any information about the X values themselves. And again, here you can use any hash function that you want, and there are actually a bunch of standard hash functions implemented in Solidity itself. Okay, so does this finally solve our problem, assuming that we put a hash function here? Well, actually, not really. So I can still do a bunch of attacks here. Let me show you one really weird attack. So let's say that, just for simplicity, 10 other people are taking part in this contract. And let's say that these 10 other people have already bought one ticket each. So I come in as an attacker, and I also buy 10 tickets. So I now own half of the tickets. I should have a 50% chance of winning the lottery. But here's the thing. After I buy the tickets and after the time for buying passes and we go into the reveal phase, I just wait for the other people to reveal, right? But now I have 10 different tickets. I can choose which subset of these tickets I want to reveal. So I can just decide, hey, I don't want to actually show my hash. I don't want to show the X value that gave me this particular hash. I don't want to reveal. Right? And if I decide that I don't want to reveal, I would change this sum here, which would basically change who becomes the winner. So by every ticket, I can just decide, am I going to reveal this ticket or not? And I have 1,024 different possibilities, because I have 10 tickets, and for each ticket, I have 2 possibilities. I can either reveal it or not. So it's very likely that I can actually find a combination of my tickets to reveal so that the total sum ends up giving me the entire price, ends up making me the winner. So actually my probability of winning this would be closer to 1. It wouldn't be 50%. And generally the problem here is that I get to choose whether I can reveal or not. Now, how can I solve this? Well, I can solve this by saying that if you don't reveal, you will never win the game, right? So I can just say, let's keep track of who has revealed and who has not revealed, and anyone who has not revealed cannot be the winner. But this is still not going to solve the problem, right? Because I have 10 tickets. Let's say I realize that if I don't reveal my second ticket, my fourth ticket will win, right? So I can just not reveal my second ticket. It works out. I'm winning anyway. Right? So this doesn't solve the problem either. Another thing we can do is to say, if anyone did not reveal, we would just refund everyone and redo the entire protocol. But even this doesn't solve the problem, because let's say that I'm someone who has 50% of the tickets. I just go through the protocol and I wait for everyone else to reveal. And then I check, would revealing make me the winner? If revealing would make me the winner, I would reveal. If not, I wouldn't reveal, and then the protocol is run again, and maybe in the next run I can win. So this actually increases my probability of winning. And if I keep doing this, I can continue until I win, so I can make my probability of winning equal to 1. So as you see, all of these have their problems, and basically we have to make sure that everyone reveals their value, because that's the only way that we can make sure they didn't cheat and they didn't try to tamper with the final value here and who the winner was. Okay, how can I make sure that, okay, so there is a question in the chat. Theoretically speaking, with 256 tickets, the buyer can always win, right? As the hash functions range is between 0 to 2 to the power of 256 minus 1. Yes, actually, that's also a really good point. So if you choose your value of X, if you just buy 256 tickets, and in one of them you choose your X value to be 1, in the other one you choose 2, 4, and generally all the powers of 2, then with these 256 tickets, you can basically get whatever value you want in the sum, and then you can make sure that you're the winner. Yes, that's true. So if you have 256 tickets, you can always win. And this is assuming that everyone else is honest and you're the only attacker. If there are several attackers, then the whole thing gets much more complicated. Now, how can I ensure that everyone is honest and everyone would reveal? Well, I can say that when you buy a ticket, other than the ticket price, you have to also pay a huge deposit, okay? And I can say that later on, if you don't reveal, your deposit will be confiscated, okay? So let's say I have this deposit here, and we will talk about what the deposit amount should be. I'm just putting some number there. So here I'm requiring that you put this deposit, and here I will actually have a function called withdraw deposit. Okay, and I just say that if you have revealed, you can withdraw your deposit. So this takes the ticket number, and I say if, let's say, the X of this ticket is not 0, basically pay the deposit to the owner of this ticket. So owner ticket.call, and the value is going to be the deposit. But I'm also going to set the X of the ticket to 0 so that I make sure I don't pay twice. Okay, and of course I want to also require that msg.sender is the owner of this ticket. Okay, and of course, again, I have to do the timekeeping. I'm not going to do it right now because we're running out of time, but we have to make sure that withdraw deposits are called before this withdraw, or if not, I have to make sure that I'm not paying the entire balance of the contract to the winner. I'm only paying the winnings. Okay, so here I should just pay the ticket price, whatever the ticket price is, times n. Okay, and then I should also set the winner to 0 before this so that I make sure I don't have reentrancy or any of those things. I need a type conversion there as well. Okay. But here's the question. So here again, I have to put, so let's say, ticket price. I have a deposit. I have also a ticket price. So now my question is, how much should the deposit be? So how much are you willing to lose in order to win a lottery? Well, the answer is the total amount of money in the lottery, right? So if I have, for example, a situation like this where my ticket price is the same as my deposit, fine, I would just cheat And if that makes me win the lottery, great. I would win the lottery and I'm just losing my deposit, no problem at all, because what I'm winning is much larger. So in this case, actually, the deposit has to be larger than the entire price of the lottery, which is crazy if you think about it. Like if a lottery is for $1 million, it means that anyone who wants to buy one ticket has to deposit $1 million just to take part in the lottery. So our lottery has basically failed at this point. We're going to talk about this in the next session and how we can fix it. I'm just going to show you one more problem with this contract. And this problem is with this for loop. So as you see here, I have a for that is going from 0 to n. So this for loop has linear runtime. Its runtime is theta n, right? But we talked about this concept of gas, and we said that whenever you call a function, you have to pay for gas. So of course, the first question is, who's calling this function? Who's calling pick winner? But let's assume that someone is calling pick winner anyway, okay? At least the person who's going to be the winner would call it pick winner. They have an incentive to do this, and they would pay for the gas. But the problem here is, how much is the gas usage? If I have a lot of participants, if I have millions of participants, then this for loop is going to run for millions of iterations. So it's going to use a huge amount of gas. But that's not the only problem. The bigger problem is that there is a gas limit for every block. So we said that the block size in Ethereum is based on how much gas the block is using. And actually the gas limit is, I think, 30 million units of gas. So in any block, you cannot use more than 30 million units of gas, which means that in any transaction, you cannot use more than 30 million units of gas, which means that if this for loop needs more than 30 million units of gas, there is no way you can successfully call this function. Whenever you call this function, it's going to run out of gas. So if you have a lot of participants, this for loop will always run out of gas, which means that your pick winner function can never be called. Because every time that it's called, it runs out of gas and it's reverted, which basically means that the money gets stuck in the contract and no one can get the money out. So this is the reason why we would never have loops like this in our contracts. So you have to always make sure that you write your contract such that every function just uses a constant amount of gas. So whenever I call a function, I have to use O1 gas. This is a bad function. I should never write something like this. Okay, so how can I fix this? Well, I can calculate my sum in this reveal function instead. So I can have a sum, which is, let's say, 0 initially. And whenever this reveal happens, I would just say sum increases by x. And I would set C of ticket to 0 as well. Okay. And then here in the pick winner, instead of having a for loop, I just take sum. Or actually, I can do the modulo n here as well. Okay. So now, as you see, every time that reveal is happening, I'm spending a constant amount of gas. I'm doing O1 work here. And then later on, when I'm doing pick winner, I'm also doing a constant amount of work. So Solidity allows you to use loops, but you should never use loops unless you're sure that the loop only runs for very few iterations. And you're sure that you can always run the loop and you will not run out of gas. Okay, see you next week.